Hi everyone, in today's video I'd like to talk about electrophilic aromatic substitution, often referred to as EAS. And this is going to be the basic substitution reactions for the simple benzene with no substituents. There are 5 of them. I'll be talking about each one and showing the mechanisms for them. As you guys can see, there are 5 main reactions with the aromatic substitutions, and the first one being halogenation, second one being nitration, the third one being sulfonation, fourth being the Friedel-Crafts acylation, alkylation, and the fifth one being the Friedel-Crafts acylation. Each one of these have their own mechanisms, but you'll see that some of these are actually very similar to each other in terms of how the catalyst works, so it'll be pretty easy once you get the hang of each one. Next, we'll be talking about halogenation. This is the basic halogenation reaction. We have our halogen molecule, and we also have a metal catalyst down here. Keep in mind the halogen can either be bromine or chlorine. The only reason we don't use the other halogens is due to thermodynamic issues and other issues as well. For our catalyst, we can have either Al or Fe as our main ones. It's completely up to you, so you can use whichever one you want. For the mechanism, we start off with, I'm going to use a bromine in our example. We're going to have a bromine molecule right here. We're going to have our metal catalyst. I'll be using Fe, and since we're using Br, we have to use Br3. We know that the bromine has lone pairs, so it's going to attack the empty p orbital of the iron. We're going to form this complex where we have our Br, and then we are also attached to the catalyst. And since the bromine donated a lone pair of electrons, it's going to have a formal positive charge. And since the iron gained electrons, it's going to have a formal negative charge. And also, this bromine right here on the end is going to also have a partial positive charge. That's important because when we actually do the reaction where we have our benzene is going to have pi electrons all around it, and one of those pi electrons can come and attack this bromine. Once that happens, it's going to dissociate from the rest of the molecule, and we're going to form this complex right here. We have our benzene once again. We're going to have 2 double bonds right there. But since the double bond to the far right attacked the bromine, it's going to lose that double bond, and instead it's going to form a intermediate like this. And we're going to form a carbocation right here since it lost the electrons. This hydrogen right here is important because it's going to be the thing that regenerates our double bond at the end. So once we have that, we should draw the FeBr4 that we also created up here. So that's just going to look like this. The iron still has a negative charge. And this is important because this is going to be acting as our base that abstracts the hydrogen, regenerating our double bond. So the bromine and iron has a single bond right here, or a sigma bond, and that's going to come and attack this hydrogen. Once that happens, we're going to regenerate our double bond right here. And the final product is going to look like a regular benzene with the halogen attached to it. We're going to create hydrobromic acid, and then we're going to regenerate our catalyst in the end. So these are the major products of our reaction for halogenation. Next is nitration. These are the set of reagents that you'll see for nitration. It will most likely be this and only this. So in order to do the mechanism, you need to know the Lewis structures of both nitric acid and sulfuric acid. So for nitric acid, we have our HO bonded to the nitrogen, which is double bonded to an oxygen, and single bonded to another oxygen. Because of this oxygen down here will have a negative formal charge, and the nitrogen up here will have a positive formal charge. We know that there are 2 lone pairs on this oxygen all the way to the left as well. As for the sulfuric acid, the Lewis structure looks like this. So our oxygen of our nitric acid is going to attack the hydrogen of our sulfuric acid. And when that happens, we're going to have these 2 complexes right here. Our formal charges are going to remain the same, but in this case, we have a formal charge of positive on the oxygen now because it lost electrons, or is now sharing electrons. And then our thing down here is going to look like this. And when this occurs, we're going to have our electrophile right here, but it's not the electrophile yet. The water is going to dissociate from the rest of the molecule, forming essentially what I just mentioned. We're going to have H2O. And then our main electrophile, which is going to be the nitrogen double bonded to an oxygen, double bonded to another oxygen, and it's going to have a formal positive charge. So now let's draw our benzene. Our benzene is going to be 6-membered with pi electrons all around it. Once again, we're going to have our electrophile floating around in the solution with a positive formal charge. And then the double bonds of the benzene are going to attack the positive charge. We're going to form this intermediate right here. Same thing like halogenation, we're going to have a cation right here, and that's a pattern that you'll see throughout all of these reactions. And then we're going to have a NO2 right here, and once again, another hydrogen right here. Okay, how do we regenerate the double bond in our benzene? Well, we created our base right here, so we're going to use that. So we have our negatively charged oxygen, we're going to have the rest of the molecule. And like halogenation, the double bond or the lone pairs of the oxygen are going to reach out and abstract this hydrogen, and we're going to regenerate our double bond right here. So essentially our final product will look like this. We're going to have our NO2, and then we're going to recreate our catalyst, which is going to be sulfuric acid. And this is the major product of nitration. Now we'll be talking about sulfonation. Just like nitration, we're going to have our sulfuric acid, and we're going to have our sulfur trioxide. And this is the only set of reagents for sulfonation. You must know the Lewis structure for each of these once more. So our sulfur trioxide is going to just be a sulfur double bonded to the 3 different oxygens. We're going to have our sulfuric acid right here. And the double bond of one of the SO bonds is going to attack the hydrogen, creating our electrophile and our base. And since our sulfur lost an electron, it's going to have a positive formal charge. And then we're going to draw our base again right here. I hope you guys are starting to see the pattern of how we keep creating our electrophile and our base. Then our benzene right here. One of the double bonds is going to attack the positive of the sulfur, or of our electrophile, creating this intermediate, and you guys should be able to predict what we're going to have. We're going to have our cation once again. We're going to have our SO3H and another hydrogen. And once we have that, we're going to have to regenerate our double bond, which the base will do. So the oxygen's lone pair is going to attack this hydrogen right here, regenerating our double bond, and our final product will look like this. We're going to have our benzene with our attached SO3H, and we're going to regenerate our catalyst at the end, and this being the major product of sulfonation. Next is Friedel-Crafts alkylation. For the Friedel-Crafts alkylation, we're going to have our R group attached to a halogen, probably Cl. We're going to have our catalyst, which is AlCl3. The mechanism for this is also essentially the same, and try to predict as we go on. So if we have our R group, which is going to be an alkyl group, let's say we use this, right? We have our catalyst right here, AlCl3. We know that the chlorine has available lone pairs. It's going to attack the aluminum, forming the intermediate right here. And once again, our aluminum is going to have a negative charge, and our chlorine is going to have a positive charge. Similar to nitration, it's going to break off right here, forming our electrophile, and we're going to have the AlCl4. We're going to have our benzene. The double bond of the benzene is going to attack the electrophile, creating our intermediate with the cation, and then we're going to add since we know that this is 2 electrons, we're going to have to add 2 carbons. We're going to have to add 2 carbons. Don't make the mistake of adding only 1 carbon by accident. Make sure you count the carbons. We're going to have our hydrogen right here, and then essentially we're going to regenerate our catalyst and abstract the hydrogen at the same time. So we're going to have our AlCl4. The bond between Cl and Al is going to attack this hydrogen. We're going to regenerate our double bond, and our final products are going to be our benzene with our alkyl group attached to it. We're going to create the hydrochloric acid, and we're going to also regenerate our catalyst. And our major product of this will be right here. One thing to know about alkylation is that many reactions happen. This is very reactive, And because of this, we're going to also have issues like carbocation rearrangement for longer alkyl chains. So whenever a chain is, let's say, longer than 3 carbons, be aware that an alkyl shift, a halogen shift, or not halogen, a hydride shift could occur. So let's use something like 1, 2, 3, 4. We're going to use butane right now. Let's say we have our carbocation right here. Since it's more than 4 carbons, we could undergo something like hydride shifts. So we know that there are hydrogens coming out of this carbon right here. And because of that, this can shift over, creating our carbocation right here. So that means our final product would eventually actually look like this, instead of just adding this onto our benzene. Like acylation, the mechanism is very similar, but unlike alkylation, you don't have to worry about carbocation rearrangements. These are mostly unreactive, so you don't have to worry about that whatsoever. So let's move on to the mechanism. We have our catalyst, which is exactly the same, and we have our alkyl attached to the acyl group attached to the halogen. So we're gonna have our acyl group, we're gonna have our catalyst. Just like alkylation, our chlorine is going to attack our catalyst, forming our complex. We're going to have a negative charge on the aluminum and a positive charge on the chlorine. And just like alkylation, we're going to also dissociate from our rest of our molecule. We're going to create our electrophile, and we're going to have our AlCl4. Or let me redraw this so that we can have our chlorine on the end. Once again, we're going to have our benzene reacting. It's going to attack the carbocation right there, forming the intermediate with the cation on the end. Then we're going to have the alkyl group, or the acyl group, attached. We're going to have our base, abstract the hydrogen once again, regenerating our double bond. So our final product will look like this. And then we're going to have hydrochloric acid, and then regenerate our catalyst. This example can be used in many ways. For example, I'm going to use a larger molecule. Let's say we have our benzene, and we have something kind of crazy like, it's not really crazy, but we just added another group at the end. Actually, we could also do this as well. So it's going to be the same process. We're going to have it react with our catalyst, forming the intermediate. Then it's going to dissociate off, creating our electrophile. And then we're going to have our AlCl4. Our benzene is going to attack the electrophile, creating what you guys already know. We're going to have 2 double bonds, a cation, and we're going to also attach this final group. Our base is going to abstract this hydrogen right here, creating our double bond once again. So our final product will look like this. We're going to create HCl and regenerate our catalyst in the end. And this will also be the major product of Friedel-Crafts acylation.